Hello everyone, my name is Guodong and I will present our paper named Leveraging Action Affinity and Continuity for Semi-supervised Temporal Action Segmentation. As we all know, frame-wise annotation of video is extremely time-consuming given the large number of the samples and their extended temporal span. In this paper, we worked with the semi-supervised setting where only a small portion of videos are annotated and the rest remain unlabeled. Our approach is based on two observations that we made on procedural videos. First, we noticed that the videos performing the same activity share a common set of actions, and there are pairs of videos with similar action temporal proportions. We term this action affinity. The other property that we observed is action continuity, which means the action labels should stay locally constant and only transit at the true boundary. While most existing temporal action segmentation models tend to oversegment actions, leading to the overfragmentation problem. Correspondingly, we introduced in this paper two novel loss functions, each attending to one of the above observations. The first one is affinity loss, which is used to impose the action prior. For a labeled video, we define the action frequency as the prior on the action composition and duration. The prior for an unlabeled video is selected from its closest peer in the labeled set, and the prior is imposed via a KO divergence loss. The second loss function, continuity loss, is designed to mitigate the overfragmentation problem. Specifically, we first subsample actions in network outputs to obtain a reduced action list without repetitive actions that are consecutive in time. We further compare the list against the predictions and use the dynamic time warping to find the optimal alignment. The continuity loss is the cost along the optimal assignment and path. Due to our deliberate selection of the KO divergence, we were able to simplify the loss to the conventional frame-wise classification loss. We further proposed an adaptive boundary smoothing technique to build more robust boundaries. Our approach is better in the following aspects. First, it uses a sigmoid shape to assign mixed probability rather than a fixed slope. And second, our soft boundary vicinity is proportional to the action duration rather than a fixed range. In our ablation end results, we found that the affinity loss alone already outperformed the naive pseudo-labeling. Adding in the continuity loss further boosted the performance. Lastly, with the boundary smoothing combined, we achieved the best performance. In the performance table on 3 benchmarks, it is noteworthy on 50 salads with 5% of labeled data. The naive pseudo-labeling approach performed even worse than the baseline that only trained with the labeled data. We speculate that this is because of the catastrophic confirmation bias from the incorrect pseudo-labels. However, our approach was able to correct them and boosted the performance by a large margin. Finally, we conclude our presentation with some takeaways. The first one is our two novel loss functions proposed for the semi-supervised temporal action segmentation task. And the second one is that we point out dense labels provide more than frame-wise supervision. They also form action priors. Last but not least, action boundaries themselves and annotations are ambiguous, so transitional action boundaries can be helpful for the temporal action segmentation task. This is the end of the talk. Thank you very much.